Hello, it's Keith here, and this is lesson 7 of the ChibiAkumas series of my Z80 programming tutorials, in which we look at how the ChibiAkumas game works and how we can change it. Now, over the next few lessons, we're going to be looking at the event stream, and this is basically the level code which makes the enemies and background objects appear in the game. Unfortunately, it's very complicated, so we're going to have to split it over several lessons. And to begin with, I wanted to do a very general overview, not particularly looking at any code, but actually just explaining how the event stream worked and what you could expect to see in it. So let's see the typical event stream of the single level that we're going to be using in these tutorials. Here it is, and you can see that basically it's a byte stream of various bytes, and you've got these definitions which are symbols that convert to a single byte as well. Now, the content is very varied, and that's kind of the problem with it. We do need to look at it from the theory first so that we understand what we're seeing. So first of all, what is the purpose of the event stream? Well, as I say, it makes objects appear on the screen during the level. Now, the most logical way would be to just have a grid sort of design with 1 byte per object. But the problem with that is if we had 16 objects tall and 256 objects wide as our sort of level map, if you will, that would actually use the entire 64K memory of the system. So obviously that's not going to be viable. So the way we've done things in ChibiAkumas is we use a event stream of timed events, because large amounts of the game level will actually have no events happen in them. So what happens is the game has an internal tick counter which constantly goes up from 0 to 255, and when it gets to 255 it rolls back to 0. So the 255 isn't a limit to the length of the level, it's just a marker for when the next event occurs. An event has a matching tick. When the events tick and the current tick line up, then that event occurs, and the event could be draw an object onto the background, create a new enemy at this height, or create a bunch of sprites, or change the background colors. So it's anything like that. So the event stream is kind of a, if you will, compressed format of all of the events that occur within the level, because the times that do not have any events happen have no bytes within the stream. So you can kind of think of the event stream being a timed scripting language where the script is entirely done in bytes, but we convert those bytes to human readable symbols so that it's easier to work out what's going on. So let's look at a typical event. So here's a single event here. Now, every event has a time, so you can see this happens at tick 15. So this would happen if it was at the start of the level, 15 ticks after the level started. There's then a command telling it that there's multiple commands here. By default, each tick only has a single command, but we can merge commands together to save memory. Actually, though, in this case, it won't save us any memory because we've wasted a second byte here with the multiple commands. So actually, we could have put 15 bank load, 15 single sprite, and we would have used the same amount of memory, but the theory still stands. So what happens at this event? Well, first of all, at tick 15, we say there's 2 commands. Then we say load in the settings from number 14, bank 14, and that will configure the next sprite that's going to be created. And then it says create a single sprite on row number 7 or column 7 if the level is vertical. So just within 4 bytes we've actually created a boss sprite using that predefined setting. And so this is how we can create very complex objects and very large number of objects in very small amounts of memory. So that's a very simple one. Well, how is that boss defined? Well, the boss was defined at the start of the level at tick 0, and we said there's going to be 6 commands at this point because we need quite a few definitions for our boss character. The first thing we do is use the command setProgMoveLife, which reads in 3 bytes. The first one is the program. The boss character doesn't have any program because it doesn't shoot. The move is to the left slowly. If you saw the lesson on moves, you'll know how that works, but 23 is basically a slow move to the left. And then the life is set to be an enemy, and the boss's life is set to 15. Then we set the sprite. It's going to be a 2-frame sprite, 2 frames of animation, and it's going to use sprite 25 here. We're adding these two together. 2-frame sprite converts to 128. The symbol is 128. So adding these two together makes a valid byte. Then we set the animator to number 10. We haven't covered animators yet, but we will. Then we tell the system we want to add this to the foreground, which effectively adds it to the end of the object list. The object list is drawn in ascending order, so objects at the start will appear in the background, objects at the end will appear in the foreground, you see. Then we set the object size. This is to do with the hit zone for collisions with the player and with bullets, so we're setting this as a 64 by 64 pixel object. And then finally, we're saving these settings into definition 14. Now you'll notice here we added 14 to load, so this compiled to a single byte, but in this case it compiles to 2 bytes. The reason for that is we expect to run this a lot of times, so we're saving a byte here. This will only be run very, very rarely, so it's a bit less efficient. We were very limited on the number of commands we could have because we were using so many bytes by the end. So that's a simple definition of an object. And you can see here there's 1, 2, 3, 4, 5, 6 lines, and there are multiple commands defined as 6 here at event 0. But we could take this first line out and put a 0 byte at the start of all of these lines, and it would work exactly the same. Also, if we really wanted, we could remove all these def Bs and put commas in between all of these. Because as I've said, these do compile just down to individual bytes. This line's 2 bytes, this line's 2 bytes, this line's just 1 byte, 2 bytes here, 2 bytes here, 1, 2, 3, 4 bytes here, and 2 bytes here. So there we go. Now, this is relating to drawing an object and defining an object, but there are more advanced commands that actually reprogram the game engine and do special things. Let's have a look at some of them here. So this is 2 simple commands you might see. One is called event call address, and then it's passed a label called set scroll down. What this actually does is it tells the core when this time occurs to call the set scroll down command within the level code. This is how things like the Zombie 2 character will have complex move patterns and special attacks. There are timed events to execute calls within the level code that allow much more advanced functionality than the game engine core could do by itself. And also we can change the current tick of the event stream, so we can make the event stream loop or jump past certain points. Just by using this jump to new time, we can set a label which will be a position within the event stream's byte data, so it could be here for example, and the current tick once that label is jumped to. But you've got to bear in mind the first tick must be after that, so if fade in was here, this would malfunction because this is 0 and this is 0. You'd need to set this to 1 or this to 255 for this to work. The tick that you define here must be before the first tick after the label. Don't worry if you don't understand this. This is a very brief introduction just so you've seen some of the code. We're now going to talk about all of the commands that are provided in the event stream, and in later lessons we're going to look at the code that makes up the event stream, and then we're going to learn how the event stream works in various levels. So you're going to see this from every aspect, but I needed to give you a very quick introduction to the code you'd see. Then I need to talk to you about all of the options, then we'll look at how those options work. Now hopefully if you're interested in programming ChibiAkumas, you'll be able to see how to change the code to make it work differently. If you're not interested in it, maybe it's going to give you some ideas of how to write very packed code with regards to defining levels and objects and events, and how to interpret that code, because as I've said before, effectively what we've got here is a scripting language that allows us to do complex events based on very small amounts of byte data. So let's have a look at pretty much all the commands that the system offers to us. Now, some commands are a single byte, some commands are defined by the top nibble, and then we add a low byte, as in this event multiple commands function here, and this event single sprite command here. So in the case of these examples here, we're going to define those as +v for value, and then you can see that the top nibble is fixed, and that is what defines event multiple commands. Some commands have a word after them, so 2 bytes. Others have a single byte. Some of course have multiple bytes, and some can have many bytes, just depending on what they are set up as. And you'll see how this all works in the later lesson when we really look at the code and how it processes these commands. So let's have a look at the commands that the core offers to us. Now, the first of these we'll look at is the add to background function. This is a single byte command, and it tells the core to add the next object to the front of the object array. This means it will appear in the background because the sprites of the object array are drawn in consecutive order, so the first sprite is likely to be overdrawn by the latter sprites. The second one is add to foreground. This adds this object to the back of the array, which means that it will be the last thing drawn or one of the last things drawn, and this means they will appear in the foreground. This is how I overcame the problem of the enemies going behind the tombstones, which is a problem with the original release of ChibiAkumas. These didn't exist before episode 2, so they didn't exist in that first release. Burst sprite is quite an unusual command. This was added with episode 2. If you remember the Sakia battle in the second level, the character exploded in a stream of hearts. Now this adds an object to that burst position very quickly. Because I was adding large numbers of objects, I needed to be able to add them to a predefined position very quickly. So that's what this does. Call address will allow a memory location to be called from within the core. This is how we can do things within our level code. We do have to be very careful though, because every register other than the accumulator is in use. So what I tend to do is I tend to use self-modifying code to modify a call within the main level loop and actually execute all of my commands then, because that way I don't need to worry about messing with the registers. So you do need to be a bit careful if you're doing very complex things here. If you're just doing a little bit of self-modifying code, you just push HL, make your change, pop HL, that'd be fine. If you're just doing things with the accumulator, again, no problem. But most times you've got to be very, very careful with this command, because all of the registers are in use by the event stream code. Jump to new time will change the current tick and position within the event stream. So that will take a label as a word and then a byte, and the byte is the new time and the word is the new position within the event stream. Event multiple commands, well, we've seen that. This is how we can have multiple commands at the same position. This was just to save having to define the tick number over and over again, because otherwise you'd have had to have the 0 tick at 6 times here. You could do that, that's perfectly valid, but we save 4 bytes by defining that there's 6 bytes at this point here. Reprogram power-up sprites. Now this is a bit of a curious one. When I started writing the ChibiAkumas game with episode 1, the first level, I realised I wanted to have the power-ups, and I needed to detect the power-ups in some way so that when the player hit them I could process them. Now I didn't have very many bytes within the object definition. I only had the 1 byte for the program, and program 3 meant it was a power-up. So I thought, well, how can I detect if they've hit a coin or if they've hit the drone power-up or the speed power-up and things? And I thought, well, I'll just detect it by the sprite number. Unfortunately, the sprite numbers were totally random at that point. They didn't really make any sense. It would have made sense to use 0, 1, 2 and 3 for the power-ups or something as the sprite numbers, but I didn't do that. It was too late. They were all over the place, really. And so I created this command that self-modifies the code of the hit detection routines to the sprite numbers for the various power-ups. Now these days I could have moved the sprites around within the sprite editor, but you've got to bear in mind when I wrote the original ChibiAkumas I didn't have the sprite editor. I was doing it with assembly language routines run from a basic program in a disk image on the CPC emulator, and it was a real pain to program and get it working. So what's very easy now with that sprite editor would have taken, you know, a couple of hours to get right, and really at the time it just seemed like, well, this will work fine. It's just a quick way of getting around it, and I don't need to worry about the problem happening again in the future. So we have to, at the start of every level, define our power-up sprites, and you can just see it here. We're defining the sprites that make up all of the power-ups just here. Now the custom moves, these are used heavily by the boss battles. What happens is when our move routine is executed, this allows us to jump out of the regular code to some special code which will directly modify the registers that make up the enemy attributes, for example the position or the fire mode or the sprite and things like that. So this allows us very complex movements, and this is how most of the boss battles were done within episode 1. With episode 2 I created the animators function, which made this mostly obsolete and is a lot easier to program complex movements without risking crashes. So it's still in there, it's still used by episode 1 version 1.666 because it was simply, it was rock solid by then, it had been debugged and it worked, so it wasn't worth rewriting it all for animators. But these days you don't really want to use these unless you've got no choice. Each one is a single word, and this is the address within the level code that will be called during the processing of the drawing of the object. Custom player hitter. Now this is used for custom player collision detection. This is used within episode 2. There's a trick on the 4th level, I think it is. You've got the vertical part within the alchemy level, and there's these stake shooters that fire stakes. Now there's actually a secret within that level. If you manage to avoid getting hit by any stakes within that level, you'll win a special unlock, and you'll get one of the characters' eye catch screens on the title screen. So that's a secret there for you. So that's one thing that can do. If you need to process the collision detection with the player in a custom way, you can put a call in here and override the collision detection. Now we've got 2 custom program routines here again, just similar to the moves. We can override certain parts of the object's events by creating a custom fire pattern if we want, using these two. We've got a hit handler here, which is used for boss battles and to allow for when you shoot the boss will register the hit. But rather than using the core's built-in life counter, it uses a custom life counter, which can be much, much larger and can do other things at the same time, like when you shoot the zombie Chu, the character will become more deformed as he becomes injured, things like that, and the Scolder character, the eye looks upwards and things. So this is how you can override the normal hit handling of the boss to allow for more complex animation and for the boss life counter to be vastly, vastly larger than the normal enemies would be. Burst position, this is again relating to that heart explosion here. So this is where we define the XY position of the character. So with regards to the Sakuya battle, what this does is it defines the position of Sakuya, and then we repeatedly use this about 30 times or something to create all of those hearts. So far more efficient than defining the XY position every time, and also far easier to program because you have to use a lot of self-modifying code within the levels to do that kind of thing within the Aku7 game engine. Full custom moves. Now this is an even more advanced version of the custom move here. This will totally override all move events for all of the objects. I'm struggling to remember where this was used. I think this was added in episode 2. There's a lot of really weird tricks in episode 2 where there's things like the exploding satellites and things. I really can't remember, but there's obviously some point where this was needed because I was totally overriding the moves code. Anyway, you'll have to bear with me on that. If I remember it, I'll put it in the comments of the website. Reprogram Palette, this is regarding to the CPC palette. At the start there's a fade in effect, and of course every level has a different raster palette. This is used to do that. It's a very complex command and it uses a varying number of bytes. There is an offset and a byte count here, and then there will be the byte count number of bytes following this. We'll have a look at this in a later lesson. It's very complex, and if you use it wrong you will corrupt the system memory, so be careful with it, or just use the templates. The plus palette, well, that allows us to reprogram the CPC plus palette. Shot to death, this is a custom hit handler for objects that have been destroyed. Again, this is relating to bonuses within the second game. There are certain objects if you shoot, like the bunny ears on the tank at the start. If you shoot them off, you will get a score. The nuke satellites, things like that. There are various objects that have events occur when you destroy them that are beyond the normal. Reprogram smart bomb. I think again this should have a word here, there's a bug there. This is again reprogramming objects for smart bombs. The nuclear satellites, again, they will explode if you use a smart bomb. Smart bomb special, this happens at the start of the smart bomb routine. This was used in the last battle because when you use a smart bomb, all of the Omega Array bullets need to disappear as well. The Omega Array bullets are held within the level code, not the core, so the core doesn't know about them. So we had to have a way of reprogramming the core to allow the smart bomb to wipe the Omega Array bullets. Reset power-ups, a single byte command. This takes away all the players' power-ups. This happens at the start of every level after a boss battle. Save last object to address. This is another clever command with regards to the boss battles. We sometimes need to be able to self-modify the attributes of the object within the code, and for example the Scolder character, we need to change all 3 of its sprites when it becomes more injured. So this is done when the object was originally created to save the address of the object within the system memory, and this allows us to do that. Set animator is a very simple command. It sets the animator for the next object, and if we are saving the settings to the bank, it will be the setting that we save to the bank. You can see it here. Again, we've not covered animators yet. We will do though, don't worry about it. Set animator pointers. The animators are a bank of data. I'll just show you that. Here are some animators here, and the pointers are a bank of pointers to the animation scripts. This defines the pointers. Again, there's a bug here, that should be W1 put in there. Set level speed. This will change the speed of the rate that the level is processed. Now, I keep describing the level events as ticks. Now, the level ticks and the internal ticks of the game engine, the number of frames being processed, are different. So there are multiple frame redraws before the next event stream tick is processed. There are times we may need to speed that up. The main one was the submersion effect of the third level. That was too slow for that immersion effect, so we turn the tick rate up faster for a moment, then turn it back to normal again. Set life and set move. These are, just like the animator, these are defining the attributes of the next object to be created. Set move life does 2 in one go, just for a bit of reduced memory usage. Set object size, this changes the resolution of the object, again relating to collision detection for bullets and the player. Set program of course is the fire mode, again a single byte. Set prog move life, well we saw this earlier, it sets all 3 main attributes to different bytes all in one go. Animator object size, they aren't included in this because they were added with episode 2. They simply didn't exist when this command was originally created. Set sprite, well that obviously just sets the sprite number. As you've seen before, we can add 128 to that sprite number to have 2 frames. We can even add 128 and 64 to have 4 frames if we want. Event settings load. Now this is a single nibble command, and a value from 0 to 14 will load a setting from that bank. If you look at save, you'll notice we're effectively adding 15, which is why this has to be 0 to 14, and that is a save command. So we've managed to have 2 separate commands within a single byte definition here, and the bank to save to is a separate byte here, whereas here it's added to the top nibble here. So that was a bit of a saving I did there. There is a second version, an extended bank, which allows for another 15 definitions. The reason I did this with episode 2 is because I had such long levels and so many enemies that just having the 14 definitions wasn't enough anymore. So that was added as a sort of extended thing for episode 2. Event single sprite is the main way we create a sprite. We saw this earlier. We created a single object at offset 7 here. Now there are other options. A value from 2 to 13 added to event single sprite will define the sprite as being on the far right, the far left, the far top or the far bottom, depending on the scroll direction of the screen. But if we don't add a value, effectively adding 0, then the next 3 bytes will be read in. One will be the sprite number and the others will be the X and Y position. Now if we add 1, then we're going to put the sprite at a different Y position on the far right, because sometimes the row options defined by this 2 to 13 aren't fine enough and we need to have a real pixel level definition. But again, it's by default the far right, but if we're scrolling left then it will be the far left or the far top, far bottom, depending on the scroll direction. All of this is handled by self-modifying code. So essentially here we've got the single sprite, which is the way we add objects, and we can add it at an exact pixel position on anywhere on the screen. We can add it on an exact Y position at the far side of the screen, or we can add it on a sort of very simplified row position. So we've got a lot of options there depending on how much memory we want to use and how precise we need to be with the sprite positioning. We've got an option here for a starburst. There's a typo there. I'm not sure this is ever used. I would have to go and check over all the code again. Maybe it's used by the Zombie Chew battle or something, or I think they may actually not be used by that. But anyway, this was one of the earliest commands I created, and it allowed a star burst to appear at any pixel position on the screen. This doesn't tend to be that useful anymore because most of the enemies are moving around so much, but it was very early on test code and I needed to see the stars working, and I think it's probably just got left in there as a sort of legacy thing. Tile sprite, now this is a more advanced version of single sprite. This allows for a grid of tiles to be added. If you want to know where this is heavily used, think of the pillars of spikes and rock. There's a pillar of rock in the first level, there's a pillar of spikes in the 4th level, and there is the angler grinder battle where there's this huge sprite which is actually made up of lots and lots of small sprites. So what we do is we add multiple objects up to 15. We provide an X and Y position and a spacing, and then enough sprite numbers to fill the number we defined, that V, up to 15. And these will be created in a strip. Now they could all link up. If our sprites are 16 pixels tall and we've defined the space as 16 pixels, you will see a grid, like you will see a constant object like that spike or that pillar of rock, that the objects all look like they're the same thing. Or we could alternatively use a 16 pixel sprite and a 24 pixel spacing, and we would have a load of separate objects. Now of course it's important to note they are separate objects. If things like the Zombie Chew is actually made up of 3 objects with 3 separate sprites, and the reason they all work in tandem and the reason they all die together is because of the custom code that's handling them. With episode 2, sprites could be much bigger, so that wasn't always the case, but even on episode 2, most of the very big objects were actually multiple sprites, just because I needed to keep the sprite size as small as possible to save memory and performance. So the bunny tank in the first level, I think that was like it was probably about 8 or 10 sprites. Each strip, one for the ears, one for the nose, one for the neck, one for each of the guns. Now you could tell that because if you shot them, they'd sort of get damaged in different stages. So you could kind of see. And then the bottom tractors, they had 4 frames of animation, where the rest only had 2. So I had to save as much memory as possible to get that into place. So what I'm trying to say is, you got to bear in mind, even if something looks like a single object, it's often a lot of separate objects, all with their own life counters, all with their own sprite numbers, all with their own positions, and it's all just about positioning all the objects together and, where necessary, making them all work together. An interesting one is the giant ghost on level 4 of episode 1. Now, in the original episode 1, that was 4 sprites that were linked together by a single death animation. So I guess that was using the custom hit handler, maybe. Or maybe the shot to death, but I think the shot to death was only added with episode 2, so it was probably just a custom hit handler. But effectively what it would do is, when any one of the 4 sprite objects that made up that ghost was shot, it would kill them all, and you would notice you'd actually get 4 coins for it because of that. Now with version 1.666, I actually changed that because I needed to do a lot of reprogramming to that anyway to get it working with the MSX. I actually reprogrammed that and used an animator, and so that was no longer necessary. So you actually now only get 1 coin. So that's an interesting quirk there. So that's all we're going to cover for this lesson. I just wanted to give you a very brief introduction to the commands and talk through the theory of what the event stream does. Now I know it's been very confusing, I apologize for that, but there's no real way of going into this very complex piece of functionality, because the event stream is essentially all of the level code, all of the new enemy creation, and a lot of the actual functionality of ChibiAkumas when it comes to the game. Even the very, very complex events like the thermonuclear exploding satellite, the complex boss battles. Most of the time it's the event stream doing all of the work, and the only reason that the last boss battle of level 5 is so much more complex than the first level of episode 1 is because the level code is tweaking the event stream and tweaking the event array, tweaking the core to allow it to do much more advanced things than it was apparently designed to do. But it's still the core and the event stream doing most of the work. It's just the levels doing tricks with that code. So I say, please bear with me with this being very complicated. We're going to go over it from every angle. We're going to look at the code in future lessons, the actual event stream source code. Then we're going to look at how to create event streams and how to configure them. So as I say, this is just an introduction. I hope you've enjoyed it, and I hope you'll follow me for the following lessons. Thanks for watching, and goodbye.